Hello everyone. I am Shrikar Venkata of National Institute of Technology, Andhra Pradesh, and I am presently pursuing Electronics and Communications Engineering, and I'm in second year. This presentation is all about home automation using Arduino, using PixSimLab Simulator, and Blynk IoT application on mobile. Now, this project is as part of my IoT internship at Emertxe Technologies, Bengaluru. So, before I delve into my project, I would like to share a few facts and learnings which I gained as part of this internship. So first things first, we learned about C programming fundamentals. We learned all about data types like char or character, occupies 1 byte of memory, then integer and float, which each occupy 4 bytes of memory, and then double, which occupies 8 bytes of memory. Then we move on to operators. Now there are arithmetic operators, which are the regular ones like plus, minus, multiplication, integer division, and the modulo, or the remain more popularly known as the remainder operator. Then we have bitwise operators like bitwise and bitwise or, and bitwise left shift and bitwise right shift. And then we learned about the logical operators like the and or and nor operators, which we predominantly use in loops and if else conditions. Moving on, we learned about conditional constructs such as if, else, in the switch case. Then we learned about loops, for loop, while loop, do while loops, and all. Then we moved on to the very important arrays concept. So we learned about how arrays are stored in C programming, and how the name of the array is nothing but a pointer to the first element of the array and all. Then we moved on to strings. Now strings are nothing but arrays of characters, but they are appended with the null or /0 character at the end. And then we learned about string functions such as the string copy, string concatenation, and string compare functions. uh, and these are like inbuilt functions of C programming. And then we moved on to the concepts of pointers, and then how passing by reference works, how passing by value works. Then we moved on to functions and recursion. We had a basic overlook of that. Then we moved on to memory segments. Now this was something new. We learned about the text segment, the where the text part of the code is stored. Then the data segment, where the regular global variables of a program are stored. The stack segment, where variables which are local to a function are stored. And the heap segment, where dynamically allocated memory such as the using calloc and malloc functions, these variables are stored in the heap section. Then we moved on to user defined data types. Now, this includes structs and unions. We learned about that, and then a bit about C++ and object oriented programming concepts such as the class constructor, methods, which are nothing but functions related to classes, and attributes, which are like variables related to classes. Moving on, we learned about the basics of embedded systems. So, what are embedded systems? So, any combination of hardware and software which is intended to do a specific task can be called an embedded system. Now, this has three parts: software, firmware, and hardware. Now, the term specific task here is quite important because, unlike computers, embedded systems perform very few and limited tasks. Now, these devices have certain peripherals such as CI, USB, SD cards, compact flash, etc. Now, classification of embedded systems. Embedded systems can be classified into a few classifications as follows. The first one is real-time embedded systems. These are strictly time-specific embedded systems, which means these provide output in a particular or defined time interval. Now, these type of embedded systems provide quick response in critical situations, and they give priority to the time in which the output is generated. That is why these are used in the defense sector, medical sector, health sector, or and the best example is a traffic control system where time is of essence. Now there are three subtypes in real-time embedded systems. The first one is soft real-time. Now, as we could see through this graph, the value drops over as a slow slope after the deadline passes. Now, the next one is firm real-time, where the value or usefulness of a data obtained from a sensor drops suddenly after the deadline and is no longer useful. The last type is the hard real type. Now in here we could see that the value or usefulness of information obtained from a sensor is in fact detrimental to the embedded system if it crosses the deadline. Moving on, the next type is standalone embedded systems. These are independent systems which can work by themselves. They don't depend on a host system, and they take input in digital or analog format and provide the output in a specified manner. So we have the well-known MP3 players, microwave ovens, calculators. All these are standalone embedded systems. Then we have mobile embedded systems. These are portable or movable. Example, the smartwatches. Moving on, we have networked embedded systems. Now, these are connected to a network which will be wired or wireless to provide output to the attached device. These devices communicated with the embedded web server through network. So, our IoT or Internet of Things should fall in this subsystem of embedded systems. Examples are ATM machines, home security systems, etc. Now we have certain other terminologies related with the embedded systems. These are like the buzzwords. We have the microprocessor, microcontroller, and SoC or system on chip. Now, all these are different when compared with each other. A microprocessor is a bare processing unit with input, output, RAM, ROM, and other peripherals connected externally. On the other hand, the microcontroller has all these integrated on a single IC. The system on chip, on the other hand, has multiple microcontrollers and microprocessors integrated on single IC, along with additional features like DSP or digital signal processing unit, radio signal processing unit, Wi-Fi modules, etc. Coming to the very important concept of memory. So we have a few types of memories associated with embedded systems. Now the first one's RAM or random access memory. This one's volatile, so this requires power supply to retain data, and this can be written over multiple times. Now there are two types of RAM: SRAM or static RAM and DRAM or dynamic RAM. Now SRAM is on one side has low power consumption and low memory capacity. It works on the basis of transistors. DRAM on the other hand works on the basis of capacitors, and though it has a higher power consumption, it has a higher memory capacity as well. Moving on to the next one, yeah, it is ROM or read-only memory. Now this is non-volatile, but the data once written cannot be erased, and it cannot be changed more than once. So there are three types of ROM. The first one's one-time programmable or OTP. The next one is EEPROM or UV ROM or ultraviolet ROM. Now we could once the data is written, it could be erased using ultraviolet rays. Masked ROM is where portions of the ROM are cut off from ultraviolet rays so that they are never erasable. There is a third type of memory which is hybrid memory. This is non-volatile but can be changed or overwritten for a particular number of times with relative ease. Now, the types of hybrid memory are EEPROM or electronically erasable programmable read-only memory. Then we have flash. Now, flash memory again has two types: NOR and NAND. NOR on one hand is byte accessible and has the feature of execute in place or XIP. So this feature is used for running the code blocks which we assign to embedded systems. And NAND on the other hand is block accessible and is used in pen drives, etc. This here is a brief overview of embedded systems. We have FPGAs, software memory, A to D conversion and D to A conversion, more on this later. Then we have sensors, actuators, then user interface, diagnostic port, an auxiliary system for cooling for efficient performance of embedded system and all. Now we come to Internet of Things or IoT. Now, Internet of Things is the network of physical objects that contain embedded technology to communicate and sense or interact with their internal states or external environment. Now, these devices range from ordinary household objects to industrial tools. So, as of present now, there are 7 billion connected IoT devices. The experts expect that this will grow to 22 billion in 2025. So, IoT is the buzzword of the embedded systems industry. By means of low cost computing, cloud, big data analytics, mobile technologies, physical things can share and collect data with minimal human intervention. In this hyper-connected world, digital systems can record, monitor, and adjust each interaction between connected things. The physical world meets the digital world and they cooperate. That's the concept of IoT. We move now to IoT architecture. So IoT architecture has three types, three regions. The first one is device connectivity. Now devices, IoT client, gateway, cloud gateway fall in this part of IoT architecture as shown here. The next one's data processing and analytics. This is the IoT solution backend. So machine learning algorithms and data processing techniques, etc., are applied here in this part of the architecture. The last one's presentation or business connectivity, where the analyzed data is sent to web applications and mobile applications for the end user. Now, IoT comes with its own set of challenges. The first one's addressing. So we use the pub sub or publication subscription methodology to counter this. So only a given set of devices can subscribe to a particular data stream, so that we don't end up pushing all tons of data to every device on the IoT network. Next, IoT systems should be scalable. We use cloud infrastructure for that. So end users need to could increase or decrease their cloud memory storage according to their needs on a monthly or yearly basis. For connectivity, we use the concept of queues. For data volume, again, we use cloud storage so that it could match up with the increasing demand for data. Now, we need embedded systems to be small in size, and for this, we cannot be quite using the famous HTTP protocol. We use an AMQP or MQTT protocol for embedded for systems requiring for usage in IoTs. So, now we move on to my project. So, first things first, what are the requirements or what are the expectations of this home automation project? So, there are three. The first one's to control garden lights on basis of sunlight intensity. So, what actually we need to do is that as the sunlight decreases as the day proceeds into night, the garden light should brighten up, and vice versa. So as night proceeds into day, the garden light should dim out slowly, and at dawn, the garden light should be switched off completely without human intervention. The next, temperature system control. So the end user should be able to switch heater and cooler on or off remotely. And additionally, the heater needs to be switched off automatically if the indoor temperature increases above 35 degrees. The third expectation is water tank control. So the end user should be able to control, should be able to switch on or off the inlet and outlet valves of the water tank remotely, preferably using his mobile phone. Now, also, if the user forgets to switch off the inlet valve once the tank fills up, the system should switch it off automatically. And also, the inlet valve should be switched on automatically if the volume of the tank drops below 2000 liters, so that the user never runs out of water. So, with these requirements in mind, we designed our home automation project. Here is the project solution. So, for garden lights, we'll be using the LDR sensor or the light dependent resistor. For temperature system, we will be using the LM35 sensor to read the indoor temperature. For water tank, we use the serial communication protocol. The microcontroller we use here is a Atmega 328P, which is embedded onto a Arduino Uno board. Now, Arduino Uno board is a all famous electronic prototyping board, and for coding we use the integrated development environment provided by open source Arduino itself. For internet connectivity of the microcontroller, we use the Ethernet Shield W5500. Mobile application for remote control will be the Blynk IoT app, and the simulation will be deployed using the PiximLab simulator, and null emulator will be used for simulating serial communication. So, first things first, garden lights. So, to control the garden lights, first we need to take an input from the sunlight detector. So now this one's we are using the light dependent resistor for this, and this is used to send sunlight and send analog signals to the microcontroller. The microcontroller adjusts brightness of garden light with respect to the analog signal sent. But how can a digital microcontroller read an analog signal? So to resolve this, we use the ADC or analog to digital conversion technique. Now, not all pins of the Arduino board are ADC capable. Only A0 to A5 pins, these 6 pins, are connected to the ADC block. Now, the ADC process has 3 steps. The first one, sampling. So sampling essentially means discretizing the x-axis of the signal. So here if we see, this is the analog signal, and this is a signal waveform. Now what we'll be doing in sampling is that we'll be discretizing the x-axis. We'll take samples of this analog signal at delta t intervals at some specified set of interval, and then we will be quantizing it. Now quantization involves discretizing the y-axis. What happens in this is that we will break up the y-axis into certain discrete levels. So each sample signal could take only a value from a given set of levels. The third step is encoding, where we will be assigning digital values to each signal level. So we previously discretized the y-axis, right? So now we will be assigning values like 0, 1, 2, 3, up to 2 raised to n. So what we up to what value we will be discretizing the y-axis depends on the resolution of the ADC. So number of encoded signal levels available depends on the width of the ADC register. Now in case of the Arduino Uno, the ADC block is a 10-bit register, and this corresponds to 2 raised to 10, which is 1024. So we will be dividing the y-axis into 1024 parts from 0 to 1023, and then we will be assigning these values to the sample signals. Now the step size obviously would be 5 divided by 1024. The value the analog signal could attain would be some value between 0 and 5 volts from the LDR sensor. So we will be dividing this range between 0 to 5 volts into 1024 parts, which corresponds to 4.88 millivolts. So the actual voltage can be calculated by multiplying the encoded signal value with the step size. So for example, we receive 1023. We will multiply it by 4.88 millivolt to get the obtained analog signal value, which would be nothing but 5 volts. Now we will be using analog read bracket pin number this function to read analog values. Though Arduino Uno has 6 analog pins or channels, only one ADC block implies only one channel can be converted at a time. Now SAR or successive approximation architecture is used in the Arduino Uno. This here is a real life LDR sensor, and this one here is the one which we use in our PixSim lab simulator. Now we are basically, after reading the data from the LDR sensor about how intense the sunlight is, we need to control the brightness of the LED lights or the garden lights. So to brighten up or dim the LED with continuous change in sunlight, analog output is needed. But digital systems cannot produce analog outputs. So the solution here is PWM or pulse width modulation, which is used to simulate an analog output. So this basically works on persistence of vision. LED is switched on and off in quick succession. Now the brightness can be controlled by controlling the amount of time the LED is on on state in one cycle of output signal. Pins 3, 5, 6, 9, 10 and 11, which are marked with the tilde sign on the Arduino board, are the only ones which are PWM capable. Pins 5 and 6 have PWM frequency of 980 Hz, while the others have a frequency of 490 Hz. Duty cycle is the percentage of time period the signal is in the on state. So obviously greater the duty cycle, greater is the brightness of LED. Now we use the analog write pin number from value function in the Arduino IDE for PWM outputs. The value should be in range of 0 to 255. Now here this graph could help us understand PWM. So what happens is the Arduino Uno microcontroller sends signals with a given predefined frequency of 490 or 980 Hz, and then the percentage of time it is in on state or off state is determined by the duty cycle which we input using the analog write function. Now the greater the value, greater would be the brightness of the LED. This here is the function which we use in the Arduino IDE for brightness control of garden light. So input valve would read the value from the LDR sensor, and this value would be divided by 4 to bring it down into the range of 0 to 255 from the range of 0 to 1024. Now this value would be subtracted from 255 because we need to apply the reverse logic. Brighter the sunlight, dimmer is the garden light, and then we would feed it to analog write function, and garden light here is the pin number to which our LED is attached to, and then we will provide a delay of 100 milliseconds. This here is the garden light setup. This is the LDR sensor, and this one's the LED light which we use for simulating our garden light. This is a block diagram. LDR sensor indirectly controls the lights with the help of the Arduino microcontroller. Next we move on to temperature system. Now here we use the LM35 sensor. Now this sensor shows an increase of 0.01 volt for every 1 degree Celsius rise in temperature. Its analog voltage input is divided by 0.01 to get temperature of the room. This temperature is then displayed on the CLCD or character liquid crystal display. Now controlling heater and cooler remotely is done through the Blynk mobile IoT app. Now using the Ethernet W5500 shield, Arduino Uno is connected to the internet. So the shield is nothing but it is an additional board which is paired up with the Arduino Uno to provide internet connectivity to our microcontroller. Firmware configuration provided by Blynk is used to connect to Blynk Cloud. So we include this part blink.begin authorization token to start up to connect our Arduino microcontroller to the Blynk Cloud, and Blynk mobile app is used on the user end of this cloud to connect to the microcontroller. Now data streams are created on the Blynk dashboard templates. Now these act like virtual pins for exchange of data between the mobile app and the microcontroller. So this here is the dashboard of Blynk. As we could see, V0, V1, V2, V3, all these are virtual pins. More on this later on. Now this here is a function which we use to read the temperature of the room, analog read of A0. Now A0 is the pin to which we connected our LM35 sensor, and we multiplied by 5 by 1023 to get the actual voltage, and then we divide it by 0.01 to get the final temperature. Now virtual pins V0, V2 created for cooler and heater toggle switches. V1 pin is used for communication of real-time temperature to the mobile app for temperature gauge display. Now we'll be displaying the temperature of the room on our mobile apps. Corresponding widgets created in developer mode of mobile app are used for this display, and V6 pin is used for display of temperature notifications. The microcontroller is programmed to shut down the heater if temperature exceeds 35 degrees Celsius and send a notification to mobile app through the V6 pin which we created earlier. Now status of the heater and cooler are displayed on the CLCD. This here is the Ethernet shield simulation, and this one's the temperature system. So this fan here acts as the simulation of a cooler, and the heater, and here is the LM35 temperature sensors output readings. This one's the block diagram. So the Arduino Uno sends the temperature to Blynk IoT app, and this temperature is received from the LM35 sensor. The Blynk IoT app instead controls the microcontroller through the heater and cooler controller pins, and the microcontroller forwards this information to the temperature system through these pins. Also, it sends notifications to the Blynk IoT app and to the CLC. These are the code snippets of the code which we use. Now this is for cooler control, digital write cooler comma control. So control is a boolean variable which is 1 or 0. So if it's 1, the cooler pin is switched on, and if it's 0, it's off. Similar for the heater pin. And now Blynk write cooler V pin. What this function does is whenever cooler V pin or the virtual pin of the cooler changes, this function is called. and here we store the state of the cooler virtual pin, whether it's 0 or 1 in the variable value. So if it is 1, we switch on the cooler and we show the corresponding display on the LCD, and if it's off, we switch off the cooler. Same for heater pin. And this function here handles the temperature gauge on the mobile app. So blink.virtual write is used to, this function is used to transfer data to the mobile app. Now this function handle temp is used to switch off the heater if the temperature exceeds 35 degrees Celsius. So if the temperature is greater than 35 and the heater switch is on or 1, the heater switch is turned off and the corresponding display is shown on the mobile app and on the LCD. Now this here is the CLCD or character LCD I am talking about. So here we display the temperature T equal to 31.3 at that time, and here we show whether the cooler is switched on or off and whether the heater is switched on or off. This here is a tab associated in our mobile app, Blynk mobile IoT app. Here is the cooler switch, here is the heater switch. Now the end user could simply press on the cooler or the heater switches to turn them on or off. I will be demonstrating this later on. And this here is the temperature gauge. It will be showing the real-time temperature of the room. And this here is the temperature notification system. So it will show whether temperature is above 35 degrees and turning off the heater, and other notifications will be displayed here. Now the last requirement is the water tank. So we will be using a serial remote tank simulator here of the Pixel Lab. Null emulator is used to set up the serial communication between Pixel Lab simulator and the serial tank. I was using the COM6 COM7 pair. In real world, the receiver pin of the tank is connected to the transmission pin of the microcontroller and vice versa. To control the inlet valve or outlet valve, we need to send a byte, either 0x00 or 0x01 respectively, followed by another byte, 0x01 to enable or 0x00 to disable. Serial.write 0x whatever the number is function is used for transmission of 1 byte at a time. 0x30 byte is sent to request data from volume sensor. Now as a response, it sends volume in 8 bits through serial communication. Now we'll be using serial.read to read these bytes. Serial.read reads 4 bits at a time or 1 byte at a time. So we need to call this function twice to read the volume of the tank. This pic here is the picture of the serial remote tank. Now this one here is the inlet valve. This one down here is the outlet valve. We could control these remotely. Now virtual pin V3 is used for displaying volume on the mobile app interface in gauge form. V4, V5 data streams, which we created earlier using the Blynk dashboard, are used for transfer of data related to on or off status of inlet and outlet valve. V7 pin is used to send notifications to terminal on app. Corresponding widgets are created in developer mode in the app. The microcontroller is so programmed as to turn off the inlet valve if the tank is filled up and turn on the inlet valve if the volume of tank drops below 2000 liters automatically, as we discussed earlier. It sends corresponding notifications regarding these events to the app too. Real-time volume of water and on or off status of inlet and outlet valve is displayed on the character LCD. This here is a block diagram. So the Arduino Uno sends information regarding volume of water obtained from the serial tank to the Blynk IoT app, and the app instead controls the inlet valve and the outlet valve through these data streams. It also sends notifications back to the app, and Arduino Uno further transfers inlet and outlet valve conditions onto the water tank so as to controlling it. Notifications and volume of the water are also displayed on the character LCD. These here are the code snippets corresponding to what we saw previously. This one's to read the volume of the tank. So we'll be sending 0x30 as we discussed earlier, so using serial dot write, and then we will be reading it in two steps. Then we will be bitwise shifting it by 8 positions, and then we will be appending value L to value H to obtain the final value. This function here is to enable the inlet wall. We will be writing 0x01 and then enabling it through 0x01 again. To disable it, we will be sending the corresponding values as we discussed earlier. This one's the void handle tank function, and this one is used to turn off the tank volume if it drops below 2000 liters, and displaying the corresponding information on the notifications tab. It also contains the functionality to switch off the inlet valve if the tank volume increases above 3000 liters, or if the tank fills up. The total volume of the tank is 3000 liters. And it also displays this information of disabling the inflow on the notifications bar of the in the app. This here is the volume which is displayed on the character LCD, and this here is the status of the inlet and outlet valve. These are the water tank notifications which we get when a certain event such as turning on or off of the inlet valve takes place. This here is the real-time water volume of the tank, and these are the buttons through which the end user can control the inlet and outlet valves respectively. And finally, this is the overall picture of my project. This one's the Arduino Uno with the Pixel Lab simulation which I showed earlier, and this one's the Ethernet shield. This is a CLCD, the LDR sensor, the garden light, temperature system, and the water tank. I would be demonstrating this in a few moments. So, thank you very much. I'm finally at the end of my presentation. Now, I will be demonstrating my project to you. So, here is the Pixel Lab simulator. Now, we need to go to modules, spare parts, to get the spare parts, or essentially the temperature system and the garden light and all. For the serial tank though, we need to go into tools, then we need to click on serial remote tank. So here we need to select the serial ports. So first we need to look at the null emulator. We need to search for setup app, and here we see that we have a virtual pair of COM6 and COM7. So we see that our Pixel Labs Arduino microcontroller is virtually connected to COM6. So we need to pair our serial tank up with COM7. I write down COM7 and connect it here. So now that it's connected, I will be restarting my Arduino Uno board. And yeah, so it's switched on, and the volume of the tank is getting filled up. The inflow is on, and in the meanwhile, while the tank fills up, I'll demonstrate the garden light. So this here is our LDR sensor as we discussed before, and this bar here is used to simulate brightness or darkness essentially. So the lower it is, the brighter is the sunlight outside. So now I click on this and I drag it upwards. So as the sunlight decreases or the brightness increases, we could see that the light, the first LED here, which is used to represent the garden light, is brightening up successively. And I increase it, and the brightness also increases with it, with the darkness, and finally it is at its brightest. Now I bring down the now I'm simulating the day. So from night it's transitioning into day, and we see that the brightness of the light is decreasing successively and switched off. So this is essentially an application of pulse width modulation, as we discussed in the slides before. Now uh, we go move on to the temperature system. So for that I would need to display my mobile screen. So here is my mobile screen. I hope it's visible, and now I will be switching on my Blynk IoT app here. So this Blynk I have designed it as to show two tabs. The first tab 1 is related to the temperature system. The tab 2 on the other side is related to the water system. So coming back to the temperature system, now if I am the end user and I need to switch on the cooler, I will be clicking on the cooler button. So I just clicked on it and switched on, and we could see that the fan is rotating now, and we also see that the cooler is switched on. This notification is displayed on the CLCD. Now I switch off the cooler switched off. Now I turn on the heater. We see that the temperature is rising, and once it is above 35 degrees, we get a notification that the temperature is above 35 degrees, and we are that it is turning off the heater, and the corresponding notification is also displayed on the CLCD. I switch on the cooler, and the temperature rapidly drops to ambient temperature. So this was the temperature system. Now moving on to the water system, to tab 2. So this here is our water tank. It's filled up now. I click on outlet valve and the water should start draining off. So we see that the water is draining off, and on the water volume here, the gauge, we could see the real-time volume of the tank. So we let it drain off, and then suddenly we get this notification: water level is less than 2000 liters and water flow is enabled. So we see that the inflow is on. We could see the corresponding notification on the CLCD as well. The inflow is on and the outflow is on as well. So if the user turns off the outlet valve, the water outlet stops and the inlet valve starts filling. I stop it, the inlet valve stops, again switch it off. Now if I don't switch it off in the appropriate time, the water should leak out, but no. uh, we have designed the system in such a way that once the water level is full, the water inflow is disabled. So we could see that it automatically cuts off. So this was all about the project, and I have displayed it in its entirety, and I hope that it was a good project. And thank you, Emertxe, for this wonderful opportunity, and thank you, viewers, all of you. Thank you.